So finally, folks, we're ready to solve our first IVP using the Laplace transform. So just as a reminder, the visualization for this is we want to solve an IVP, and we're solving that IVP in the t domain. And what we're going to do is we're going to map this IVP over to the s domain, and what we'll see is that it becomes an algebraic equation. We're going to solve that for capital Y sub s, and then we're going to map it over with the inverse Laplace transform. So Laplace transform takes us over from the t domain to the s domain. The inverse transform will take us back to where we'll have the solution that we're after for this IVP. So all of this, one more time, is occurring in the time domain, and all of this is occurring in the s domain. If you're not quite sure what I mean by these t domains, s domains, that's okay. We're just getting an introduction to this topic. All right, here we go. We're ready to go ahead and take the Laplace transform. And what we're going to do is we're going to take the Laplace transform of both sides of this ODE. So the Laplace transform is linear, which means on the left-hand side I can rewrite it as the Laplace transform of y prime plus 3 times the Laplace transform of y. Now careful, the Laplace transform is linear, which means it distributes over the addition between these two functions, and I can factor scalars out of it, but that's all I can do. And then on the right-hand side, we've got the Laplace transform of e to the 7t. So we just did some work where we showed that the Laplace transform of y prime for some function y would be s y sub s minus lower y sub 0 plus 3, and then we don't know what this Laplace transform is yet because we haven't solved for the unknown function, but we'll call it y sub s. So here we've got the Laplace transform of y prime gave us this, and the Laplace transform of y gave us y sub s. And then we need to also take on the right-hand side, we need to compute the Laplace transform of e to the 7t, but we did that. For e to the 7t. We actually derived that from the definition in an earlier example. Remember that this had the condition that s needed to be greater than 7 for this to hold. Okay, it may not look like it, but what I have here is now an equation that I can solve for the unknown function y sub s. Why is that? Well, let's do just a little bit more clarification here. We've got s y sub s, and notice that that's the minus y sub 0, but that's just the initial condition to this IVP. So we've got minus 2 plus 3y sub s is equal to 1 over s minus 7. So all I need to do now is solve this equation for y sub s. So let's go ahead and do so. I'm going to collect together all the y sub s terms on one side and take all the non-y sub s terms over to the other side. Then I can factor on the left-hand side, I can factor out the function y sub s. Now what I can do is I can divide the s plus 3 over to the other side. So this gives me y sub s is equal to 1 over s minus 7 times s plus 3 plus 2 over s plus 3, where I divided s plus 3 into both of these fractions. Now, at this point, what I'd like to do is I'd like to apply the inverse Laplace transform and get us back to the t domain. The problem is, and this is often what occurs here, is I might recognize this as having been the Laplace transform of some function. But this is a little too complicated. And so what we will have to do is we will have to take these expressions on the right-hand side and rearrange them into terms that we know how to take the inverse Laplace transform of, meaning we will recognize that they came from being the Laplace transform of some function. So we'll explain more of this as we go along, but right now what I definitely need to do is I'm going to go ahead and separate this fraction through partial fraction decomposition so that I have the two factors separated by addition. So I can rewrite this as y sub s is equal to 1/10 over s minus 7 plus negative 1/10 over s plus 3 plus 2 over s plus 3. So folks, if you're rusty on the technique of partial fraction decomposition, you're going to want to review that because we're going to be doing it over and over again in these Laplace transforms. So at this point, we haven't had any practice of converting or calculating inverse Laplace transforms, and we're going to spend a chunk of time learning how to do that. But if I were to rewrite this as y sub s equals 1/10 times 1 over s minus 7, minus 1 over 10 times 1 over s plus 3, and I could have combined those two fractions together, plus 2 times 1 over s plus 3. Each one of these looks like having done the result of a Laplace transform. And in fact, that's going to set me up for being able to convert this back to the t domain. So I'm going to go ahead and take the inverse transform of each side of this equation. So we're taking the inverse transform of y sub s and the inverse transform of the right-hand side, 1/10 times 1 over s minus 7 minus 1/10 times 1 over s plus 3 plus 2 times 1 over s plus 3. So the inverse Laplace transform of capital Y sub s is just the original function y sub t. You should feel okay with that, right, folks? Because we said when we take the Laplace transform of y, it gives us capital Y sub s. So if I do the inverse transform to capital Y sub s, that should bring me back to y sub t. Then we have the linearity of the Laplace transform. So and that also means that its inverse is linear. And so we can say that's 1/10 times the inverse transform. Let me keep that as red just to be consistent. Times the inverse transform of 1 over s minus 7. And I'll just fill this out. And so now I can take the inverse transform of each one of those functions, and I recognize this as simply being the result of having done the Laplace transform of e to the 7t. That should look familiar. That's how we got that original 1 over s minus 7. So when I did the Laplace transform to e to the 7t, that's what I ended up with. So when I do the inverse Laplace transform of 1 over s minus 7, I get back to e to the 7t. Likewise, I get minus 1/10. This would be e to the, careful, watch your sign there, minus 3t plus 2 e to the minus 3t. And I'll do now something I could have done quite a while back. We get y sub t is equal to 1/10 e to the 7t. I can combine these two. This is negative 1/10 plus 2. So that would be plus 19/10 e to the minus 3t. And what I have here is the result of solving this original initial value problem. Notice that I don't find a solution. Generally, I don't find a solution to the ODE. Instead, what I do is I find solutions to the specific IVPs. So I didn't find the general solution to the ODE and then plug in the initial condition. And in fact, the initial condition was sort of built into the process of solving for my capital Y sub s. And so when I get my solution back, what I have is not a general solution to the ODE, but the specific solution to this given IVP. And we've done so with this technique of Laplace transform. So just in summary, and this is what we're going to spend the rest of the course working on, we took a IVP in the time domain. We applied the Laplace transform to it. That gave us an algebraic equation that we had to solve in the S domain. That was this algebraic equation right here. And we had to solve for the function y sub s. We then had to do some algebra, and we solved for the function y sub s. Here I've finally written it, I guess here's where I parked it. There's where I've solved for capital Y sub s. And then I did the inverse transform to both sides of this equation. And on the left-hand side, I recovered that y sub t. And on the right-hand side, I then have the particular solution to this IVP. This is tough, folks, but we're going to get a lot of practice with this. But rather than slowly building up to it, I wanted to start off right off the bat with showing you how these problems will work. And this is about as fast of an introduction to it as I could do. All right, folks, I'll see you in class next time. Let me know if you have any questions.